Welcome! In this video, I'd like to talk about some basic graphs and some properties that you need to know before you start a calculus course. We start with linear functions, which are straight line graphs. For the first case, y equals c, where c is any real numbers, it is called a constant function. Its graph is a horizontal straight line parallel to x-axis going through y equals c value. For example, with y equals negative 2, it should be going through y equals negative 2 and looks like a horizontal line. For the domain, which is also called input or x value, we can take any real number, and the range, which is output value, should be just negative 2. In our second case of straight line graphs, x equals c. Its graph is a vertical straight line parallel to y-axis going through x equals c value. For example, the graph of x equals 3 should be going through x equals 3 and appears as a vertical line. For the domain, we can take only a single value as x equals 3. However, we can take any real numbers for the range. Please note that this is not a function. The third one is a general form of straight line graph. It has an equation y equals mx plus b, with a slope m and y-intercept of b. The slope is a ratio of change in y and the change of x. If the slope m is positive, then the line is right side upwards, and if it is negative, then the line is right side downwards. We can take any real numbers for the domain and range. Let's take a look at a couple of examples for the third type. The first one is y equals 2/5 x minus 4. Since the slope 2/5 is positive, we have a right side upwards graph for this. We can take any real numbers for the domain and range. First, start with the y-intercept. Plot a point on y-axis at negative 4. And then from that point, we can move 5 steps horizontally and 2 steps up vertically. There is another point there. We then connect it with the y-intercept to draw a straight line. This is the y equals 2/5 x minus 4 graph. The second one is y equals negative 3x plus 4. Since the slope is negative, we have a right side downward graph this time. Although it is not necessary, let's change the slope into fraction form. Again, we can take any real numbers for the domain and range. As before, we begin with the y-intercept. Plot a point on y-axis at 4. And then, from that point, we move 1 step horizontally and 3 steps down vertically. There is another point there. We connect it with the y-intercept to draw a straight line. This is y equals negative 3x plus 4 graph. Next, let's move to the graph of quadratic functions. For these functions, it's a parabola. Y equals ax squared plus bx plus c as the standard form, and the vertex form is as shown. There the vertex is at hk. If the leading coefficient a is positive, then the graph opens up. In this case, we can take any real numbers for the domain. However, the range is restricted. Its y-value starts at k, which is at the vertex, and goes up to infinity, including the k-value. This is why there is a square bracket on the left side and an interval notation. On the other hand, if the leading coefficient a is negative, then the graph opens down. Similar to positive case, we can take any real numbers for the domain. However, the range is less than or equal to k-value. The axis of symmetry is going through x-coordinate at the vertex, which is h. So its equation is x equal h. In order to find the x-intercept, we need to find the root by solving the quadratic equation. The y-intercept is straightforward as it is just a constant term of the function. All we have to do is simply substitute x equals 0 into the function to find y-intercept. Let's take a look at a couple of graphs for quadratic functions. First one is y equal x squared minus 4x plus 3. This can be written in vertex form, as shown. If you are curious about this conversion, please watch a separate video called Completing the Square from my YouTube channel. It shows how to convert from a standard form to a vertex form in a step-by-step manner. For this case, there is a vertex at 2, -1. So we can plot a point at 2, -1 as the vertex. Since the leading coefficient 1 is positive, this graph opens up. In this case, we can take any real numbers for the domain. The range is restricted. Since the y-value at the vertex is -1, it starts from -1 and goes up to infinity. To find x-intercept, we need to find the root by solving the quadratic equation. For our example, we'll use the factoring method to solve the equation. Again, if you need a refresher on this method, please watch a separate video called Solving Quadratic Equations by Factoring. We get 2 roots by letting each factor equal to 0. Let's plot these 2 points on x-axis. For the y-intercept, since the constant term is 3, it is 3 on the y-axis. The axis of symmetry is going through the x-value of the vertex, so x equals 2. Now we connect these important points, and we can use this information to create a graph of y equals x squared minus 4x plus 3. For our second example, we'll go over the graph for y equals negative 2x squared minus 8x minus 7. Since the leading coefficient is negative, we know this graph opens down. This can be written in vertex form as shown. For this example, there is a vertex at -2, 1. So plot a point at -2, 1 at the vertex. Again, we can take any real numbers for the domain. The range is restricted. Since the y-value at the vertex is 1, the range starts from 1 and goes down to -infinity. To find the x-intercept, we need to find the root by solving the quadratic equation. This time, I will use the quadratic formula method. we can find the two roots by using the formula. Let's plot these 2 points on the x-axis. For the y-intercept, since the constant term is negative 7, it is negative 7 on the y-axis. The axis of symmetry goes through x value of the vertex, so x equals negative 2. Now we connect these important points and using information to get the graph of y equals negative 2x squared minus 8x minus 7. Next, let's take a look at exponential functions, which we can see many applications. The basic form is as shown as b as the base. The base must be positive and cannot be 1. Similar to previous functions, we can take any real numbers for the domain. However, the range is restricted. Its y values are all positive real numbers for y equals b to the x. If the base is greater than 1, then the graph is increasing. On the other hand, if the base is between 0 and 1, then the graph is decreasing. In either case, there are no x-intercept. Since the x-axis becomes the asymptote for either graph. Recall that an asymptote is a line where the graph approaches but never touches as it moves toward either positive or negative infinity. Lastly, the y-intercept is 0, 1 for either case as long as the function has a form of y equals b to the x. Now we'll go over some examples for the graph of exponential functions. Let's begin with y equals 4 to the x. The base 4 is greater than 1, so the graph is increasing. Just in case, we can take a few points to draw the graph. If x is negative 1, then y is 1/4 or 0.25. At x equals 0, y is 1 as the y-intercept. And if x equals 1, then y value is 4. We know the graph approaches the x-axis as it moves toward the negative infinity. So y equals 0 is the asymptote. Using all guidelines, we can draw y equals 4 to the x as shown. For the second function, the base is half, which is between 0 and 1 value, so it is a decreasing graph. Again, take a few points to find each y value. If x is negative 1, then y is 2. At x equals 0, it is a y-intercept. And if x equals 1, then y is 0.5. Also, we know the graph approaches the x-axis as it moves toward positive infinity, so y equals 0 is the asymptote. Using all guidelines, we can draw y equals half to the x as shown. For either case, the domain is negative infinity to positive infinity, and the range goes from 0 to positive infinity, not including 0. There are no x-intercept since the x-axis becomes an asymptote for either graph. Next, let's find out what happened to the graph when we replace the variable x with negative x. In our first example for y equals e to the 2x, the base is e, which is approximately 2.718. The base e is greater than 1, so the graph is increasing. As before, we can take a few points to draw the graph. if x is negative 1, then y is approximately 0.135. At x equals 0, y is 1, which is also the y-intercept. And if x equals 1, then y value is about 7.39. We know the graph approaches the x-axis as it moves toward negative infinity, so y equals 0 is the asymptote. Using all guidelines, we can draw y equals e to the 2x as shown. For the second function, we replace 2x with negative 2x. Again, take a few points to find each y value. If x is negative 1, then y is approximately 7.39. At x equals 0, it is the y-intercept. And if x equals 1, then y is about 0.135. The asymptote is y equals 0 as well. The curve approaches the x-axis as it's moved toward positive infinity. Using all guidelines, we can draw y equals e to the negative 2x as shown. The graph is decreasing. If we replace x with negative x, then we can see the two graphs are symmetric about y-axis with each other. Please note that we can rewrite the function e to the negative 2x as quantity 1 over e squared to the x. So the second graph is the base between 0 and 1 case. That's why it is indeed a decreasing graph. Next, I want to highlight the connection between exponential and logarithmic functions. Here is a graph of y equals e to the x. When we try to draw its inverse function, the function is symmetric about y equals x. Here is the inverse graph of y equals e to the x, which is called y equals natural log of x or ln x, which is a logarithmic function. So the inverse exponential function becomes logarithmic functions. There was a y-intercept at 0, 1 of y equals e to the x. However, 1, 0 becomes x-intercept for y equals ln x function. Also, the range was restricted as positive for the exponential functions. Now, the domain is restricted as positive for the logarithmic functions. Lastly, let's take a look at equation of a circle. The circle is all the points that are at the same distance from the center. The standard form for the equation of a circle is shown with the center at h, k and the radius r. In this standard form, it is easy to recognize and graph a circle. However, you may see another form, which is called general equation form as shown. When you see this form, you need to convert it to the standard form by using the completing the square method. To calculate the domain for a circle, we use the x value at the center, h minus the radius for the left limit, and h plus radius is the right limit. Both h values are included, so it should be expressed as a square bracket when using the interval notation. Likewise, to calculate the range, we use the y value at the center, k minus the radius for the left limit, and k plus radius is the right limit. Again, both h values are included. To find the x-intercept, let y equal 0 and solve for x, and x equals 0 to solve for y for the y-intercept. Please note that, unlike previous graphs, this circle cannot be a function as it fails the vertical line test. When a vertical line is drawn and the line meets more than one point, then it is not a function. Lastly, let's take a look at a couple of examples for a circle. Since this is in the standard form already, it is straightforward to graph. But just in case, make the y term clear, since the standard form indicates the minus sign before h or k. Here is the proper form to get the information we need. The center is at 5, -1. Please make sure not to include the minus sign after the x or y and only take h or k part. The radius R is 4, not including the squared part. To calculate the domain, we use the x value at the center, which is 5 in this case, and the radius is 4. For the left limit, 5 minus 4 to get 1, and 5 plus 4 to get the right limit of 9. Both edge values are included, so it should be expressed as a square bracket and an interval notation as shown. Likewise, to calculate the range, we use y value at the center. -1 minus the radius 4 to get the -5 for the left limit, and -1 plus radius 4 equals 3 is the right limit. Again, both -5 and 3 are included. As for the x-intercept, substitute 0 into y and solve for x. If you solve this quadratic equation, we can get approximately 1.127 and 8.873 as the two roots. If you're not sure about how to solve this equation, please watch a separate video called Solving Quadratic Equation by Completing the Square Method to see a step-by-step tutorial. For the y-intercept, substitute 0 into x and solve for y. However, this equation does not give real number solutions. Let's draw this. Plot the center at 5, -1, and 2 intercept we found. Here is a circle with the radius 4. Just make sure that the domain is between 1 and 9 inclusive. For the range, we can see they are between -5 and 3 inclusive indeed. Let's take a look at the last example. Since this is not in the standard form, we need to convert it into the standard form using the completing the square method. If you're not sure about this method, please review the video, which is called Solving Quadratic Equation by Completing the Square Method for more examples. First, separate the x and y terms and move the constant to the right side of the equation. To complete a square for each group, begin by taking half of the coefficient of x term and add the square of that value on both sides. Similarly, take half of the coefficient of y term and then add the square of that value on both sides. Now factor each group. Simply take x and half of the x term to get the complete squared form for the x term group. In the same way, we can complete a square for the y term group. For the right side of the equation, simplify the 3 terms to get 9 and express it as 3 squared. Now we have expressed it in standard form. The center is at 1, 2. The radius r is 3. To calculate the domain, we use the x value at the center, which is 1 in this case, and the radius 3. For the left limit, we have 1 minus 3 to get the negative 2, and 1 plus 3 to get the right limit of 4. Likewise, to calculate the range, we use the y value at the center. 2 minus the radius 3 to get the negative 1 for the left limit, and 2 plus radius 3 equal 5 is the right limit. Let's now draw this. Plot the center at 1, 2, and here's the circle with the radius 3. Again, make sure the domain and the range are as we calculated. This general equation form is not easily recognizable as a circle, but it is. I hope this video has helped in preparation for starting a calculus course smoothly. Thank you for watching. See you again.